If you were to compress Earth's entire history into a single calendar year, modern humans would appear in the last 30 minutes of December 31st. So clearly, relative to Earth's history, we are a new species. And yet, we've already managed to fundamentally change the planet. So now, more than ever, it is vital that we take a look at our climate history and the novel solutions that could shape the future of climate science. Over the last 4.5 billion years, life on Earth has worked its way through a natural cycle of evolution, diversification, and occasionally collapse. Among the most devastating of these collapses was a mass extinction event that occurred around 252 million years ago that eradicated 96% of marine species and 70% of terrestrial ones. We refer to this catastrophe as the End-Permian extinction, or fittingly, the Great Dying. But what caused such a widespread loss of life? Well, in a recent study, Stanford researchers found that the End-Permian extinction is likely characterized by increasing greenhouse gases due to ongoing volcanic eruptions. These carbon and methane emissions, the study found, contributed to mass extinction by inducing global warming, ocean acidification, acid rain, and the depletion of the ozone layer. This should sound familiar, because these same End-Permian emissions that once ended 3/4 of all life on Earth are strikingly similar to the nature of human-induced greenhouse gas emissions. So, when we look at the End-Permian, we have a lot to learn, because researchers suggest that in the next 70 years, we will reach 20% of the End-Permian. We have become the volcanoes of the End-Permian era. Humans are manufacturing the conditions for a 6th mass extinction event. So now more than ever, it is imperative that we look at the Great Dying and what we can learn from it. So what can we learn from the Great Dying? Well, first, the End-Permian extinction teaches us the importance of climate tipping points. Tipping points in the context of climate change are thresholds in the climate system that can cause irreversible changes when crossed. According to research by the University of Leeds and China University of Geosciences, the key tipping point that accelerated mass extinction during the Great Dying was the dieback of tropical rainforests. And here's why it's important. We're seeing that same tipping point being approached today. If it progresses, the dieback of the Amazon rainforest could cause severe climate shifts. The same phenomenon holds true for the Arctic ice sheet, which is warming nearly 4 times faster than the global average and has already lost enough ice in the last 2 decades to flood the entirety of the US. We need to pay special attention to these climate tipping points before changes become irreversible. Second, marine collapse may be exponential. During the Permian, ocean stratification and anoxia were some of the earliest signs of collapse, and we're starting to see similar trends today. According to an Earth and Planetary Science letter study, the End-Permian extinction suggests that our climate system may respond non-linearly to extreme CO2 levels. This means that our current climate systems could actually be underestimating risk, and that we shouldn't necessarily interpret ocean stability as resilience. This shows us that we need to treat our ocean ecosystems with greater urgency, because biological collapse may seem subtle in its early stages. And as our oceans begin to stratify, we're actually fast-tracking deep sea mining, which the Center for Biological Diversity called a, quote, environmental disaster in the making. And if that weren't comforting enough, the End-Permian extinction suggests that carbon feedback loops make global warming self-sustaining even after emissions halt. A one-earth study done in affiliation with Ripple and colleagues suggests that our climate models demonstrate that even cutting emissions may not be enough to fully reverse warming past a certain point. So this has major implications because it implies a need to redefine climate risk in terms of feedback activation zones rather than just temperature targets. This means that we have to pay attention to things like methane release, soil carbon loss, and ocean acidification in order to prevent tipping points from being crossed. Now, we already know the importance of mitigating risk in destabilized regions, so bioremediation and reforestation efforts have us headed in the right direction. In a recent project I did regarding ocean pollution, I researched the ecological stability of coral reefs. And as I researched mitigation strategies for coral reef systems under chronic exposure to persistent organic pollutants, I noticed a promising finding in the efficacy of certain microbial communities for pollutant degradation. According to a study published by the European Geosciences Union, for instance, certain reef microbes have a very high catabolic versatility, which means that they are much better than others at breaking down harmful pollutants. This means that by facilitating the breakdown of otherwise persistent pollutants, these tiny microbes have the potential to significantly reduce the pollutant load taken on by reef sediments. This has implications for future bioremediation plans, as reef zones can be selectively inoculated with these optimized microbial communities in order to improve ecosystem resilience. Still, climate models suggest that unless we begin enacting these types of unique plans, what we're doing just isn't enough. Which brings us to a controversial climate solution that has recently worked its way into mainstream climate discourse: geoengineering. And when you picture geoengineering, you may think of these massive space mirrors that deflect sunlight away from the Earth. And while this is a real idea, it's mostly theoretical. Things like carbon capture, which involves capturing and storing atmospheric carbon, and marine cloud brightening are more solidified plans. Marine cloud brightening, or MCB, is a geoengineering technique that involves spraying sea salt aerosols into the atmosphere in order to increase the reflectivity of low marine clouds to deflect sunlight back into space, thereby reducing surface temperatures. And just last year, a group of researchers attempted to conduct an MCB trial in an effort to marginally cool the atmosphere. But the trial was almost immediately shut down due to mistrust and negative public perception. Now, geoengineering tends to get a bad rep because what most people fail to understand is that geoengineering isn't actually about creating this miraculous cure-all that must be implemented. It's about understanding technological intervention in order to inform current and future climate solutions. So by ignoring geoengineering or incorrectly writing it off as a moral hazard, we risk overlooking potentially vital solutions and failing to get the full picture. During the Permian, tipping points made the climate crisis irreparable. That's why geoengineering is so important to study. If we reach similar tipping points, geoengineering solutions may become necessary to buy time. So here's the key takeaway. Our national climate pullback is a dangerous step in the wrong direction, and the time to act is now. And this means cutting emissions, funding science, and garnering public support for climate solutions. We all have a part to play in shaping a livable future, for ourselves, but especially for the future generations, who are forced to deal with the long-term consequences of our current climate decisions. So I urge you to ask yourself what you can do to create a more livable planet, whether it's demanding stronger climate policy, supporting conservation efforts, or simply changing your own habits. We all have a part to play, and every action matters. So let's learn from the End-Permian, act with urgency, and contribute to a climate future in which humans and the planet can coexist comfortably. Because unlike 252 million years ago, we have